This is the last section of Unit 6 that we're going to do. It says polynomial functions, and rational functions are not a polynomial function, but most textbooks will put this in with polynomial functions because we're looking at different characteristics of functions. So this is going to be different from all the other functions, and I think that might be where some of the difficulty lies for some students. So a rational function is a fraction of a polynomial. So we call it a ratio, but a ratio is a fraction. And there's a polynomial in the numerator and there's a polynomial in the denominator. The domain of all rational functions is all real numbers except the values that make the denominator equal to 0. So we've done this already. At the very beginning, we reviewed rational functions and we looked at this. So I don't care at all about the numerator. I'm just looking at the denominator. So if I set the denominator and say that it cannot equal 0, and I solve, I get x cannot equal 7 for this first example. For the second example, the denominator is already factored. If it were not factored, and it could be factored, you would need to factor it. So I set each factor not equal to 0. So for the first one, divide by 3, well, it's 0, so I get x cannot equal 0. Subtract 5, I get x cannot equal negative 5. Add 1, divide by 2, I get x cannot equal 1/2. So it's 3 values. It's going to be all real numbers except those 3 values. And if you wanted to do interval notation, you're welcome to. I'm perfectly happy with this. If you were taking some kind of a multiple choice test, maybe a placement test for college or something like that, you might see in interval notation. So for example, this one here, x cannot equal 7. Well, it means it's everything but 7. So it starts from negative infinity, goes to 7, does not include 7, and then it goes from 7 to infinity. To me, it's a lot easier just to write that. Rational functions might have vertical asymptotes. They don't have to, but they may. So to get the vertical asymptote, it's very much like the domain. I look at the denominator. I don't care about the numerator. So with this one here, I'm going to set the denominator equal to 0. So I get x equals 7. This one has to be written in the form of an equation. A vertical asymptote is a vertical line. So if you were to graph this, coordinate plane 1, 2, 3, 4, 5, 6, 7, that's what your vertical asymptote looks like. If you just tell me 7, that's not enough to get any credit for it. This next example I have, you need to look at the numerator and the denominator. If I factor the numerator, I get x plus 5, x plus 3. Now notice there's a similar factor in the numerator and the denominator, that x plus 5. So that's not going to be a vertical asymptote. That's actually a whole. So it's not a vertical asymptote. It actually has a coordinate for a point, but I'm just introducing this to you right now. You may or may not have gotten this in Algebra 2. If you go on higher in math, you'll learn more about this as well. So my only vertical asymptotes are going to be from this 3x equals 0. So I get x equals 0, and this 2x minus 1 equals 0. So I get x is equal to 1/2. This one has 2 vertical asymptotes. Now the next one are horizontal asymptotes. And horizontal asymptotes are not difficult. Most people don't remember them. So what happens in a horizontal asymptote is there are 3 different cases. If the degree in the numerator is less than the degree in the denominator. In this case, it's always going to be y equals 0. So come down here, these 3 examples, my degree in the numerator is a 1, the degree in the denominator is 1. My degree in the numerator is a 2. Oh, but in my denominator I have a 3x times an x, so it's 3x squared times a 2x. that's going to be 6x cubed. So x squared, oh my goodness, x squared in the numerator, x cubed in the denominator. So the degree in the numerator of 2 is less than the degree in the denominator of 3. So this is going to be y equals 0. The degree in the numerator, so n, is equal to the degree in the denominator, n equals m. This is going to be y equals, and it's going to be the leading coefficients. It's going to be some number. So let's come down this first example. The degree in the numerator is a 1, and the degree in the denominator is a 1. Okay, that means they have the same. That means n equals m. So it's going to be y equals 3 over 1. Always reduce your numbers. So it's going to have the horizontal asymptote y equals 3. And the last case occurs when the degree in the numerator is greater than the degree in the denominator. So this last example, obviously, is degree of 3 in the numerator, degree of 2 in the denominator. In this case, there are no horizontal asymptotes. There are slant asymptotes. And that will leave for another year. I would have to find that using long division. So it's one of the reasons you were taught long division. Okay, we're going to do some graphing of these, and during the live lesson I'll give you more detailed graphs, but this is just transformations of them. So if you have a specific rational function, the 1 over x, it's called a parent graph. You could do transformations from that function, but this is one of the harder ones to do transformations from. So if I had 1 over x, I would look at this and say, okay, my horizontal asymptote is going to be y equals 0. My vertical asymptote is going to be x equals 0. So grab a different color pen. You can't see it very well because it's going to be right on the x-axis and right on the y-axis. Then I could pick points. It doesn't have any x-intercepts or y-intercepts. And if I were to pick a point, the only point that's really good is this 1, 1 and negative 1, negative 1. The rest are all fractions or decimals, and they're really hard to find good ones. So this is what's going to happen. It looks like this. If I graph it in the calculator, it's very deceiving. So 1 divided by x so you can't really see it very well. It actually keeps going to the left and keeps going to the right. There's asymptote there, and there's vertical asymptote there. It's kind of hard to see. If I took away let's take away the axes. So I'm going to go down, turn the axes off. You can see it a little bit better. It really does continue to go. You just can't see it very well. So when we're talking about transformations, you have horizontal transformations. 1 over x minus c. If c is with the x, it's going to go right c. If it's a plus c, it goes left c. 1 over x and then plus c is on the outside of the function. Since the function is 1 over x, this is saying f of x plus c. This is going to go up c. If c were negative, it would go down. We could do vertical stretches and shrinks also. So in this case here, if c is greater than 1, it's a stretch. And if it's a number less than 1, but it's got to be positive, so it's got to be greater than 0, it's going to be a shrink. And there's a way to do horizontal with this too, but it's not going to really affect you much in this course. Okay, and then the y-axis reflection and the x-axis reflection. It doesn't matter which one you use, because one's going to be negative 1 over x, and the other one's going to be 1 over negative x. And they come out to be the same thing. Let me change that. 1 over negative x. So we're really not going to talk about reflections in this course. This is truly just a little extension of what you did in Algebra 2. So when I graph these, I can use these transformations and what I did before. So the first thing I notice is that this equation here has moved right 3. So I know my vertical asymptote is going to be x equals 3. My horizontal asymptote is still going to be y equals 0. And then I'm just going to take these points. This one that's at 1, 1, it's going to move over here to 4, 1. And this negative 1, negative 1 is going to move 3 over to 2, negative 1. And I just can't get any other good points. It's going to look like this. This example here, 1 over x plus 2, is going to go up 2. So if it goes up 2, my vertical asymptote stays at x equals 0, and my horizontal asymptote is going to go up 2. So it's going to be at y equals 2. Plot these points again, because I'm not really changing anything else. And that's what it looks like. This f of x equals 2 over x, that's a vertical stretch. So my x-axis and my y-axis are still going to be my vertical and horizontal asymptote. So the asymptote. The y-axis is the line x equals 0. The x-axis is the line y equals 0. But I'm not going to be at the point 1, 1. This is a stretch, so that means I have to change the y value. I'm going to be at 1, 2. Negative 1, negative 2. And then it's got that same general shape. And the last one, I'm going to move left 1. So that means my vertical asymptote moves left 1. I move down 4. So my horizontal asymptote moves down 4. And then I'm just going to plot those 2 points again, because it's not worth trying to find any other good points.